You can do it if you believe you can. Hi, everyone. In this video, I would like to go through all the major topics for grade 11 university math, test number 8, exponential functions. The three major topics are solving for x, graphing f of x, and word problems. Before we begin, it's important that you track your progress. As we're going through some of these examples, you can give yourself a check mark if you fully understand the entire example, or you can put an X next to it if you have no idea how to do it yet. And of course, sometimes there's that in between case where you're thinking you kind of get it, but you still want to practice, and you can put that question mark as well. Let's begin. Example number 1, solve for x, show all work for full marks. Now we're giving you 5 cases for number 1, A, B, C, D, and E. But what I would like to do is over-deliver and do a little bit more. So the idea is I'm going to do one. I would like you to do one. That way you can feel confident and competent. So for 1A, it says 4 to the power of 5 equals to 4 to the power of x. One of the exponent laws states that when you have the same base, you can equate the exponents. So 5 equals to x. That's it. If this is something that you understand, give yourself a check mark. And now I'm going to give a question for you to try on your own. And of course, I'll take this up after you press play, which means you can pause in a moment. So let's say we give you 3 to the power of x equals to 27. So again, you can pause the video. When you're ready, press play again. I'll be here. Welcome back. So again, the first step is to recognize. On the left-hand side, it says 3 to the power of x. On the right, it says 27. The same base is going to be 3. So for example, 27 is the same as saying 3 times 3 times 3. So 3 to the power of 3. Again, when you have the same base, you can equate the exponents. X equals to 3, just like that. Now, again, I would like to over-deliver. If you want to get perfect, what I'm recommending for every student is to double-check. I'll grab a different color for you. Double checking just means you grab a calculator or you can do mental math, and you're basically saying if x really equals to 3, I'm going to go back to the left-hand side and plug in 3. And if I do this right, I should get the same answer as the right-hand side. So 3 to the power of 3 is 27, exactly the same as the right-hand side. Now you know you have the perfect solution. Example 1b. 32 to the power of x divided by 4 to the power of x plus 2 equals to 16. So again, the first step is you have to find a common base. Think about 32, 4, and 16. The common base is not 4. The common base is going to be 2. So when you think about 32, this is the same as 2 to the power of 5. Again, if you want to grab a calculator to confirm that, 2 times 2 times 2 times 2 times 2 is going to be 32. And of course, 4 is 2 squared, which you want to put in brackets. 16 is 2 to the power of 4. So again, the first step is to express it with a common base. Now, if you think about the second step again, I can copy the right-hand side, 2 to the power of 4. On the left-hand side, there's a power to a power. So 2 to the power of 5 to the power of x means you multiply the exponents, 2 to the power of 5x. If you look at the denominator, here's the mistake that some students may make. I'm going to show you what not to do and what to do as well. So if you think about power to a power, you're going to multiply 2 with x, so 2x. And some students may think it's 2x plus 2. So again, the mistake is you have to make sure you draw the arrows. If you are thinking the answer is 2x plus 2, that means you have to go back, put the arrows back in to give yourself some guidance, because 2 times 2 is going to be 4. So the correct answer should be plus 4. So when you erase the mistake, 2x plus 4, that is the correct answer now. Again, here's another mistake that I see all the time. When you have 2 to the power of 5x divided by 2 to the power of 2x plus 4, many students recognize you're subtracting the exponents, but they do it like this. They write down 5x minus 2x plus 4. And again, this is not the right answer yet. Don't forget brackets. Go back, put the brackets. Now you're on the right track. So if we continue, that's going to be 2 to the power of 5x minus 2x minus 4, which equals to 2 to the power of 4. The difficult part is now over. When you have the same base, you can equate the exponents. So I'm going to continue here. And of course, if you think about 5x minus 2x, that's going to be 3x minus 4, which equals to 4. What does that mean? When you bring negative 4 to the right-hand side, that's 4 plus 4, that's going to be 8. The opposite of multiplying by 3 is to divide by 3. So x is going to be 8 over 3. Again, that is not enough if you want to get 100%. I'm inviting you to double check. What does that really mean? I'm going to erase everything in part A. I hope you've been copying it. You're not eyeballing the video. Really important that you make that hand-eye-brain coordination. So again, in a different color, I'm saying you can double check, which means you plug in x equal to 8 over 3. So on the left-hand side, we look at this and we say 32 to the power of 8 over 3 divided by 4 to the power of 8 over 3 plus 2. So I'm going to grab the calculator. I hope you're doing this with me. Here we go. I turn it on. I press clear. 32 to the power of 8 over 3. Divide this by 4 to the power. You can put brackets around that. 8 over 3 plus 2. When I press equal, in one step, I see 16, which is exactly the same as the right-hand side. Again, in case you're not sure why double checking matters, is because double checking gives you the best feeling, which means you got perfect while doing your assessment of learning. Now, before we keep going, of course, I'm going to give you another question. I would like you to try this first, all by yourself. And when you're ready, I'm going to take it up. So 81 to the power of 2x plus 7 divided by 27 to the power of 3x minus 2, which equals to 3 to the power of 0. So again, pause the video, try this. When you're ready again and you press play, I'll be here. Welcome back. I'm going to erase some of this so there's space before I take it up. All right. So again, in a very similar structure, the first step is you have to find the common base. 3, 81, and 27. The common base is going to be 3. 81 is 3 to the power of 4. Don't forget brackets. Write down 2x plus 7. If you look at the denominator, 27 is 3 to the power of 3. Don't forget brackets. Write down 3x minus 2. And of course, 3 to the power of 0 can copy it as is. Now, I'm not going to do the arrows anymore. I want to see if you can stick with me in terms of the next step. Think about power to power. You're going to multiply. 4 times 2x is going to be 8x. 4 times 7 is going to be 28. If I look at the denominator, 3 times 3x is going to be 9x. 3 times negative 2 is going to be negative 6. And of course, this equals to 3 to the power of 0. Again, I'm going to continue in the next column here. Don't forget you can subtract exponents. Now, of course, there's also another method, by the way. If you prefer cross multiplying, that works too. So again, I'm going to give you two choices here, and I'm just going to show you one of them. Either can subtract the exponents on the left-hand side and keep the right-hand side as 3 to the power of 0, or a slightly faster way really is you can cross multiply, because if you kind of go back and look at 3 to the power of 0, that's really 1, right? So if you did cross multiply, which is totally fine, you would have 3 to the power of 8x plus 28, which equals to 3 to the power of 9x minus 6. The difficult part is now over. Same base, you create the exponent, exactly what we did in part A. Again, you should be able to solve for x now. You bring 9x to the left, 8x minus 9x is negative x. You can bring 28 to the right, negative 28 minus 6 is going to be negative 34. X equals to 34. Again, please consider double checking. I'm not going to force you to double check, but I'm going to show you the power of double checking. So again, I'm going to go back and say, well, if I'm doing this right, that means if I plug in 34, I should get the other side. So on the left-hand side, I go back and I am thinking 81 to the power of 2 times 34 plus 7 divided by 27 to the power of 3 times 34 minus 2. I'm going to grab a calculator and work it out here and now. Now, on my calculator, I did notice it didn't give me an answer because this calculator is not powerful enough to work out these large numbers. Let me grab another calculator. Now, if you do enter this into the calculator, assuming a calculator can hold this capacity, this will give you the same as the right-hand side, which should equal to 1, just like that. Example 1c. 3 to the power of x plus 1 plus 3 to the power of x plus 4 equals to 252. So again, step 1, you want to think about factoring. I'm going to write this for you. Factoring is a very useful skill in terms of solving this type of question. What I really mean is you want to factor the term with the smaller exponent. So for example, if you think about x plus 1, you think about x plus 4, the question becomes which exponent is smaller. And of course, x plus 1 is smaller, so you're going to factor 3 to the power of x plus 1 to the front in the brackets, and you want to be mindful here. What times 3 to the power of x plus 1 will give you 3 to the power of x plus 1? And the answer is going to be 1. Plus, if you think about 3 to the power of x plus 1 times 3 to the power of something will give you x plus 4. So don't forget the first exponent law. When you have the same base, you can add the exponents. X plus 1 plus 3 will give you x plus 4. So again, this is how you know you're on the right track. You can grab a calculator. I'm going to do some mental math. 1 plus 3 cubed is 1 plus 27, which is 28. I can even put this at the front if I like. And of course, the opposite of multiplying by 28 is to divide by 28. So again, I'll grab a different color for you, and I'm just going to divide both sides by 28. And of course, on the left-hand side, 28 divided by 28 is going to be 1. On the right, again, you can do mental math. You can grab a calculator. 252 divided by 28 is going to be 9. So notice the question is no longer as difficult as it was from the first step. 9 is the same thing as 3 to the power of 2. So again, 3 to the power of x plus 1 equals to 3 to the power of 2. When you have the same base, you can equate the exponents. X plus 1 equals to 2. X equals to 2 minus 1, which is exactly 1. Now, how do we know we're doing it right? Again, not to overstate this, you can go back and double check. So on the left-hand side, this is going to be equal to 3 to the power of 1 plus 1 plus 3 to the power of 1 plus 4. Again, you can grab a calculator. I'm going to take 3 to the power of 2 plus 3 to the power of 5. When I press equal, I see 252, which is precisely the right-hand side. Again, I would like you to try one more on your own before we do part D. So I'm going to erase the original question, of course. Here's the new one I would like you to think about. And yes, I'm going to keep the same hint, which is going to be factoring. So you're going to try 4 to the power of x plus 1 plus 4 to the power of x plus 4, which equals to 1040. So again, pause the video. When you're done and you press play again, I'll be here. Welcome back. So again, the first step is to factor. You want to factor the smaller exponent. If you compare x plus 1 with x plus 4, the smaller exponent is going to be x plus 1. What that means is you have 4 to the power of x plus 1 times, in brackets, again, what times 4 to the power of x plus 1 will give you 4 to the power of x plus 1? Well, the answer is 1. Likewise, if you think about 4 to the power of x plus 1 times 4 to the power of something, will give you 4 to the power of x plus 4 back. When you multiply the same base to add the exponents, x plus 1 plus 3 will give you x plus 4 back. So again, this equals to 1040. You can grab a calculator or you can do mental math. 1 plus 4 cubed is 1 plus 64. So you can write down 65 at the front, just like that. And again, the opposite of multiplying by 65 is to divide by 65. What that means is on the left, 65 divided by 65 is 1. On the right-hand side, you can take 1,040 divided by 65, which is going to be 16. Don't forget, the common base is going to be 4. Now, if you're thinking, what if the common base is 2? Can I do that? You could, by the way, but 4 is faster. So 16 is going to be 4 times 4, which is 4 squared. If you have the same base, you can equate the exponents. X plus 1 equals to 2, which means, again, x equals to 1. In case you're not double checking at all, I'm going to try this one more time. I'm not going to double check every question in this video, but I would like to just invite you just enough for you to decide how badly do you want to get perfect. So if you want to double check, you go back to the left-hand side and you're thinking, if x is 1 and I plug it back in, I should get exactly the same as the right-hand side. So again, I grab the calculator, 4 to the power of 2 plus 4 to the power of 5, and I see 1,040, precisely the same as the right-hand side. So again, I'm not going to double check anymore, but if you don't double check and you don't get perfect, ask a simple question. Do you know how to get perfect? And the answer is yes, which means the only question left is, why didn't you double check? Example 1D, 4 to the power of 2x minus 20 times 4 to the power of x plus 64. So again, this is the question where in a similar way you're factoring, but it's not the same type of factoring. So I'm going to write down the word factoring again to remind you, but the major difference is in part C, it was common factoring. Whereas in part D, this could be sometimes simple factoring, sometimes it's complex factoring, sometimes it's a perfect square. It depends, but it's a different type of factoring. And what I mean is this. Now, for some students, you're going to say, I don't get this. Can I kind of let A equal to 4 to the power of x? This step is optional. You don't need to do this, but if this adds value to your understanding, go for it, right? Because if A equals to 4 to the power of x, then A squared is going to be 4 to the power of 2x. So again, when you square both sides, power to power means you multiply, and x times 2 is going to be 2x. So this means you can rewrite this in terms of a squared minus 20a plus 64, which equals to 0. Again, this is simple factoring. This is grade 10 math in a grade 11 course. So a squared, of course, is a times a. You think about 64, and negative 16 times negative 4 is going to be positive 64. Negative 16 plus negative 4 is going to give you negative 20. So now you go back and you say a is 4 to the power of x minus 16. And again, 4 to the power of x minus 4, just like that. I'm going to draw a line in the middle. I'm going to divide this into 2 different columns. I'm starting with the last one first. 4 to the power of x minus 4 equals to 0. This means 4 to the power of x equals to 4 to the power of 1. Same base, equate the exponents. X is going to be 1. If I go back to the first column, 4 to the x minus 16 is going to be 0. 4 to the power of x equals to 16. And of course, 16 is the same as 4 squared. So in this case, x is going to be 2. If you would like to double check, go for it. And if not, that's okay too. Before we hop over to the next example, I would like you to try one more. Here we go. I would like you to try 3 to the power of 4x minus 10 times 3 to the power of 2x plus 9, which equals to 0. Pause the video when you're ready and press play again. I'll be here. Welcome back, everybody. So in this case, I'm going to go straight to factoring. So again, if you want to let a equal to 3 to the power of 2x, that's fine. You don't really need to do that. So I'm going to see if you can follow along. I hope you can. This is more of a grade 11 skill, which will help you in grade 12 math. So when you think about 3 to the power of 4x, you can break this down as 3 to the power of 2x times 3 to the power of 2x. Again, not to overstate this, when you multiply with the same base, you add the exponents. So 2x plus 2x will give you 4x back. When you think about positive 9, that's the same as saying negative 1 times negative 9. That multiplies to 9. Negative 1 plus negative 9 gives you negative 10, so you factored it. Again, I'm going to draw a line in the middle, divide this into two different columns. In the first column is going to be 3 to the power of 2x minus 1 equal to 0. This means 3 to the power of 2x equals to 1. This is exactly example 1a. So 1, of course, is the same as 3 to the power of 0 in this case. You have the same base. You can equate the exponents. You can solve for x. So if 2x becomes 0, x equals to 0. In the second column, 3 to the power of 2x minus 9 equals to 0. 3 to the power of 2x equals to 9. The common base is going to be 3. So when you think about 9, think of it as 3 times 3 or 3 squared. Again, same base, equate the exponents. 2x equals to 2. The opposite of multiplying by 2 is to divide by 2. So x equals to 1. Again, if you would like to double check this, please do so. We're moving forward. Example 1e. 5 to the power of 3x squared plus 5x plus 30 equals to 5 to the power of 2x squared plus 2x plus 58. Step 1, notice it's the same base. You can equate the exponents. So write down 3, x squared plus 5x plus 30, which equals to 2x squared plus 2x plus 58. Now, before we keep going, you want to be mindful. If you begin with the end in mind, reverse engineer. Because it's x to the power of 2, you're going to get two answers. Sometimes it's two different answers. Sometimes it's two identical answers. But nonetheless, in general, you're expecting two answers. So I'm going to bring everything to one side, equate it to 0, and solve for x. 3 minus 2 is going to be 1. So you're going to have 1x squared. On the left, you can cross this out if you want to stay organized. 5 minus 2 is going to be 3. So you can write down 3x. You can cross this out. And of course, 30 minus 58, that's going to be negative 28, just like that. Again, this goes back to simple factoring. When you think about x squared minus, or I should say x squared plus 3x minus 28, x squared becomes x times x. When you think about the factors of 28, or negative 28, I mean, that's going to be negative 4 times positive 7, because negative 4 plus 7 will give you 3 back. Again, I can divide this into two different columns. X minus 4 is going to be 0. X is going to be 4. In the second column, x plus 7 is going to be 0. X is going to be negative 7, just like that. Again, I'm strongly inviting you to double check if you want to get 100%. Let's give you one more to practice. And here's the question. 2 to the power of 4x squared minus 5x minus 28, which equals to 2 to the power of x squared plus x plus 1. Pause the video, try this place. When you press play again, I'll be here. Welcome back. So the first step again is you can equate the exponents because you have the same base. So 4x squared minus 5x minus 28 equals to x squared plus x plus 1. Step 2, again, x squared means you're expecting two different answers, or two answers in general. You're going to bring everything to the left, equate this to 0. 4 minus 1 is going to be 3, so 3x squared. To stay organized, you can cross them out in pairs. Negative 5x minus x is going to be negative 6x. And if you think about negative 28 minus 1, that's going to be minus 29. Now, in this question, notice it's slightly different. In fact, this is a lot more intense because if you look at this, sometimes you can put it in factor form. Sometimes you have to use the quadratic formula. So let me double check this quickly to see if this one even works, because I'm going to check the discriminant, b squared minus 4ac let's see. Now, x equals to negative b plus or minus the square root of b squared minus 4ac divided by 2a. So in this case, the values of A, B, C are 3, -6, and -29. So I'm going to go back. I'm going to plug in -6 for B, -6 for B here, B squared minus 4 times A times C divided by 2A. Okay. Now we're expecting 2 decimals. We can round this to 1 decimal place, which means if you do double check, you're going to get the approximation. You're not going to get the exact answer, which is fine. Now let's see what happens if I take 6 squared minus 4 times 3 times 27. That should be the square root of 384 divided by 6. Okay. So I'm expecting decimals. And again, I'm going to round to 1 decimal place. In the first case, this is going to be 4.265986324, or approximately 4.3. And of course, in the second case, if I plug it back to the calculator, this is going to be approximately -2.265986324, or approximately -2.3, just like that. So again, sometimes you get decimals, not a big deal. You just got to grab a calculator and work it out. We are making progress. Question number 2. Graph the following function, state the transformation, and clearly label a minimum of 3 points. This means you can label 4 points, 5 points, more than 5 points, but we're expecting 3 points minimum. Now, if you really look at this, there are a couple of things you can do. The most basic concept is to go through a TOV, table of values. That's what we're going to do right now, just to demonstrate this. So you can create a table, and you can pick a couple of numbers. So I'm going to recommend 5 numbers. And of course, if you want more than 5, that's fine. But I think 5 is enough for the purpose of this example. So in the first column, you can write down x. You can use -2, -1, 0, 1, and 2. And y equals to 3 to the power of x minus 2 plus 1. Now again, you're going to round some of these answers to 2 or 3 or 4 decimal places, depending on the number. You also want to leave it in exact form. So when x is -2, that's going to be 3 to the power of -2 minus 2 plus 1. Now, if I grab a calculator, this is the same as saying approximately 1.01. So I'm going to round to 2 decimals in this case. In the display, I actually see 1.012345679. If I plug in -1, that's going to be 3 to the power of -1 minus 2 plus 1. And again, this approximately equals to 1.04. If I plug in 0, that's going to be 3 to the power of -2 plus 1. So again, this is going to be approximately 1.11. If I plug in 1, that's going to be 3 to the power of 1 minus 2 plus 1. So this equals to 3 to the power of -1 plus 1, which is approximately 1.3. And of course, if I plug in 2, this is going to be 3 to the power of 2 minus 2 plus 1. That's going to be the same as saying 1 plus 1, which is 2. Now, there's also something you want to think about, right? When you state the transformation, you discover you can actually pick even better numbers to illustrate this. So I'm actually going to pick 2 more numbers. You're going to see why I'm doing this once I state the transformations for you. So again, I'm doing more than I need to, but I think it's important to always think about the basic numbers, -2, -1, 0, 1, and 2, before you think about the faster approach. If you think about x equal to 3, that's going to be 3 to the power of 3 minus 2 plus 1. That's going to be 3 to the power of 1 plus 1. That's going to be 4. And of course, if you plug in 4, that's going to be 3 to the power of 4 minus 2 plus 1. That's 9 plus 1, which is 10, which is beyond the scope of the graph. So if I begin with the end in mind, I'm going to go back to the graph, and I'm going to say, well, -2 will give you approximately 1.01. So again, I'm just going to put it there. I'm going to label this point, by the way, -2, 1.01. If I pick the next point, -1 will give 1.04. If I go to 0, that's going to be 1.01. 1, 1. So I'm going to label this point 0, 1.11. When x is 1, that's going to be 1.33. Now notice that, actually, let's go back. Let's put this a bit more accurate for you. 1.11 is going to be somewhere there, actually. This one's going to be there. When x is 1, that's going to give you 1.3. When x is 2, y is going to be 2. I'll label that point. And of course, when x is 3, it's going to give you 4. I'll label that point as well. Again, the question says minimum 3 points. So notice I didn't label every point. Now, don't forget the horizontal asymptote. And the horizontal asymptote is going to be at y equal to 1. You can connect these points, draw a line, draws 2 arrows, label the function. Now, don't forget the state of transformation. So I'm going to grab a text box and talk about why it's better to do it in this new method. So I'm going to grab a text box. I'm going to type in the transformations. One of them, of course, is x minus 2 means you go right by 2. So you have to write down horizontal, translation, 2 units, right. And of course, the plus 1 means you're going up by 1, vertical, translation, 1 unit up. Let's put this right here. Now, here's the last idea before you try the next one. Because we know you're going to go right by 2, up by 1, what that means is you could have focused with this in the middle because you're going right by 2. So you could have also just picked numbers from 0 to 4 instead of -2 to 2. But I did want to give you the basics in case you want to just get a start with step 1. Example 2b. I would like you to try this. This is y equal to negative, open bracket, 1/3, close bracket to the power of negative x. Pause the video when you're done and you press play again. I'll be here. Welcome back. So here's the first step, everybody. Before you graph this, I'm going to say simplify this. What I mean is if you think about the exponent, negative x, and you think about the fraction 1/3, you can make this positive. So instead of negative x, you make this positive x by rewriting it as 3 to the power of x. So again, the question is y equal to negative, in brackets, 1/3 to the power of negative x, which equals to y equals to -3 to the power of x. So again, in this case, if I go back to the same table of values, we can definitely use -2, -1, 0, 1, and 2 this time. And that's going to be more than enough. Oops, 1 second. Okay. Let's go back to the same page. Let's continue here. Let's grab the same color for you. Okay. So again, if you go back and you plug in x to be -2, this is going to be 3 to the power of -2. Don't forget the negative at the front. So -3 to the power of -2 approximately is going to be -1/9, which is really approximately -0.1. I'm going to round it to 1 decimal place. If you plug in x to be -1, that's -3 to the power of -1, which is going to be 1 divided by 3. So it's going to be -0.3. When you plug in x to be 0, that's going to be -3 to the power of 0. This is going to be -1. If you plug in x to be 1, that's going to be -3 to the 1, which is -3. And of course, when you plug in 2, that's going to be -3 to the power of 2, which is -9, which is beyond the scale that we have on the graph to the right. So again, I go back and I can start with the horizontal asymptote, which is going to be y equal to 0. -2 means go left by 2, down by 0.1. And I'm going to label this point. So this time I'm going to label more points for you. If I go left by 1, I can go down by 0.3. When x is 0, you can go down by 1. When you go right by 1, you can go down by 3, just like that. And of course, I'm not going to graph to -9 because that's beyond the scope or beyond the scale that we have, which is fine. Don't forget to label this. When I do label this, by the way, I always label the original. I don't label the new function, because if you did make a mistake, by the way, then you're copying the mistake onto the graph. Now it does say state the transformation. So I'm going to grab a text box, go back and type in the fact that this is going to be reflected with respect to the x-axis. That is the one transformation for this graph. Example 2c, again, I would like to try this first. Y equals to 2 to the power of -x minus 3. Pause the video. When you're done and you press play again, I'll be here. Welcome back, everybody. Now that we did 2 graphs for example number 2, we're going to show you a shortcut. The shortcut starts with the asymptote. So what I'm saying is, if you look at this, it says -3. So this is telling you there's going to be a horizontal asymptote, specifically at y equal to -3. So the first step you could take is go straight to -3, label this graph, and write down y equals to -3. Now, of course, you still want to simplify this. So you can go back and say y equals to half to the power of x minus 3. And now you're looking at exponential decay with a y equal to -3 horizontal asymptote. And again, if you're more comfortable with the table values, by all means, you can use this for this case as well. I'm going to copy this. Again, let's try a couple of points. Okay. I'm also going to show another approach, by the way. So I always give you 5 points, but if you want to go minimum, if you're asking what is the least I can do just to show the graph, well, instead of going from -2, -1, 0, 1, and 2, you could also take -2, 0, and 2 as well. It's not recommended, but I still want to show that to you, just for those students who are thinking, I need 3 points. I'm going to give 3 points on the graph, and that's it. So in that scenario, you can say half to the power of -2 minus 3 equals 2. Again, that's going to be equal to 1. So half to the power of -2 minus 3, that's going to be 1. If you plug in 0 in this case, that's going to be 1 minus 3, that's going to be -2. And of course, if you plug in 2, that's half to the power of 2 minus 3. We will get a decimal, and that's okay, by the way. That's going to be -2.75. So what I mean is, if you go back to the graph now, and we grab the same color for you, I go left by 2, and I go up by 1. So it's going to be -2 and 1. If I go to 0, I'm going to go down by 2. That's 0, -2. Last but not least, if I go right by 2, it's going to be down by 2.75. So I'm going to label this 2, -2.75. Again, I can connect them just like that. I can label the original function just like that. And of course, don't forget to state the transformation. So there are 2 ideas. One of them we factored in. So the other idea goes as follows. You can write down -3 really means go down by 3. So vertical translation, 3 units down. Just like that. One more graph before we do word problems. Example number 2, part D. Now this is a bit more intense. So again, I would like you to try this first. Y equals to half times 3 to the power of x minus 4. Pause the video. When you press play again, I'll be here. Welcome back. So again, we did 3 graphs. I'm going to go straight to the fastest approach, and you can use this, of course, as well. So sometimes you can start with the transformations. So for example, there's a half at the front. This really means there's a vertical compression by a factor of half. So you can say vertical compression by a factor of half. You can say 0.5 as well. Notice in exponent, it says x minus 4. This really means shift it to the right by 4. You can say horizontal. Translation, 4 units right. Again, I'm just going to leave it right here. Let's expand this a little bit. There we go. Okay. Now, in terms of the horizontal asymptote, since there's no vertical translation, the horizontal asymptote is still going to be at y equal to 0. Now, the other idea is, notice we're going right by 4. So the better TOV, now that we did a couple of examples, is you don't say -2, -1, 0, 1, and 2. You go back and you recognize I'm going right by 4. And if you're going to go right by 4, you can put 4 in the middle. So you can pick two numbers that's smaller than 4, two numbers larger than 4. So one example could be 2, 3, 4, 5, and 6. Again, this will make perfect sense once you practice a couple of examples, exactly the way we're doing it here. Again, if I start in the middle, half times 3 to the power of 4 minus 4 is the same as saying half times 3 to the power of 0, which is half times 1. That's going to be half. If I plug in 5, that's going to be 5 minus 4 in the exponent. So it's going to be half times 3, which is 1.5. Again, if you want to express everything to decimals, you could. So maybe instead of writing half, I'll write down 0.5 so you can see it in decimal form. If I plug in 6, this is going to be 3 to the power of 6 minus 4. This is going to be 3 squared, which is 9. 9 divided by 2 is 4.5. This will still fit into the graph. And of course, you can also plug in the first two numbers. So for example, half times 3 to the power of 2 minus 4. If I grab a calculator, this is 3 to the power of -2 times half. So it's going to be approximately 0.1. It's actually 0.05555 repeated, but I'm going to round it to 0.1. Likewise, if I plug in 3, it's going to be half times 3 to the power of 3 minus 4, which approximately is going to be 0.2, just like that. So I go back to the graph, and I can start with 6, 4.5. So I'm going to label this 6, 4.5. I can go to 5, 1.5, which would be there. If I look at the next point, 4 and half is going to be roughly there. Now again, since you have to graph minimum 3 points, if all you have are these 3 points, that's fine. The other points are going to be something like that. And again, don't forget to label the function y equals a half times 3 to the power of x minus 4, just like that. And that is the graphing section of this video. Example number 3. There are 4 word problems we're going to practice. Some of them have multiple parts. So for number 3, the question says a population triples every 10 years. Presently, the population is 20,000. A, find the population in 25 years. B, when would the population be 200,000? And C, when was the population 2,000? So let's write this by first drawing a number line. So it depends on the problem. And what you really want to think about is time equal to 0. And this could be any time in the timeline. Imagine you're pressing start on a timer, or I guess a stopwatch. And in this case, we're saying, okay, in the beginning, time is going to be 0. And we want to find out what happens later on. So for example, in part A, they're asking, find the population in 25 years. So you want to find out what happens when t is going to be 25. So now, in part A, I'll grab a different color for you. The first step is to write down the formula, which we talked about, is A equal to I times B to the power of T divided by P. Now, it doesn't have to be these exact notation, by the way. You can kind of express it however you like. As long as you have the same meaning, then that's the most important part. The rest is going to be the same, no matter how you kind of plug it in. Okay. Now, in the first case, it says a population triples. So triple means B is going to be 1 plus 2. So if you want, you can write down 1 plus 2, but really it's going to be 3. And how often does this happen? It triples every 10 years. So P, which is the period for, in this case, for the population to triple, is going to be 10. So you're going to make this 10. Now, presently, the population is 20,000. That means I is going to be 20,000. And in part A, they're asking, find the population, meaning find the amount, in 25 years. So time is going to be 25. So again, I'm going to grab a calculator. I'm going to work this out with you. We're going to round this. We'll talk about the rounding in a second. 20,000 times 3 to the power of 2.5. So again, if you work this out, this equals to 31 or 311,000. 769.1454. Let me just double check the math here to make sure my numbers are correct. 3 to the power of 25 divided by 10 multiplied by 20,000. Yep, that looks right. And of course, you want to think about the rounding. So when it comes to time, you want to round up. When it comes to people or living things, you want to round down. So you can't really have this 0.1454 of a person. So I'm going to say, please consider rounding down 311,769 people. In part B, they're asking when will the population be 200,000? So again, in part B, the future population is going to be 200,000. Of course, when I say future, sometimes it could be the past, sometimes it could be the future. But since 200,000 is larger than the present population and it triples, that's the future value, right? And this equals to the present, the initial amount, which is 20,000. Again, if the population triples, it's going to be 3 to the power of. Now, when means you want to find time. So you want to find t divided by, again, in this case, 10. Now, to solve this, you have to use log, which we'll get to. Step 1, the opposite of multiplying by 20,000 is to divide by 20,000. So on the left, or I should say on the right-hand side, 20,000 divided by 20,000 is 1. On the left-hand side, you can cross it the 4 zeros. And 20 divided by 2 is going to be 10. So now you go back and you want to solve for the exponent. And the only way to solve for the exponent is by taking the log of both sides. So again, one of the properties of a logarithmic function, and there are 8 properties, but the one you're responsible for is the exponent can be brought to the front. So again, log 10 equals to t divided by 10 times log of 3. Now, I'm going to write this out in one step here. I hope you're with me. The opposite of dividing by 10 is to multiply by 10. So 10 times log of 10 divided by, again, the opposite of multiplying by log 3 is to divide by log 3. And we're going to talk about the rounding as well in a second. So you can grab a calculator. You can work it out. Of course, log of 10 is 1, by the way. And when you work this out, this is going to be approximately 20.9590327 so 20.96 years. Now, if you're rounding it to the nearest whole, and we'll tell you what to round, officially on the assessment of learning, but if you round to the nearest whole, I'm going to say it's better to think about this in terms of 21 years, which guarantees at least that amount. So something that I want to think about when it comes to time, round up. When it comes to living things, round down. For part C, it's asking when was the population 2,000? So this is now obviously in the past because 2,000 is smaller than 20,000. So it didn't happen, or it's not going to happen in the future, but it happened in the past. So for part C, you will write down 2,000, which is the population from before. The present population is 20,000. Again, 3 to the power of t divided by 10. The opposite of multiplying by 20,000 is to divide by 20,000. Again, on the right-hand side, that's going to be 1. On the left-hand side, 20,000 divided by, or 2,000 divided by 20,000 is going to be 1 over 10. You can write down 1 over 10. You can write down 0.1. It's up to you. Don't forget, you have to log both sides in order to solve the exponent. And of course, in grade 12, you can also ln both sides. That's another approach, but we'll stick to this method. You can bring the exponent to the front. So now log of 0.1 equals to t divided by 10 times log of 3. Let's create some space. So now, if I keep going, let me just write this out again. T divided by 10 times log of 3. So t equals to, the opposite of dividing by 10 is to multiply by 10. So 10 times log of 0.1 divided by log of 3. So again, I'm going to grab a calculator. I'm going to work it out with you. We'll talk about the rounding as well. 10 times log of 0.1 divided by log of 3. This is going to be negative 20.96 years. So you can round this to negative 21 years. And the more important note is that negative means before, right? So if I grab a text box, I'm going to write in the space about 21 years in the past. If it's positive, you're talking about future. If it's negative, you're talking about 21 years from before. So again, not to overstate this, but if you go back to the timeline, see, I can kind of update this a little bit. If I said time equal to 0 was in the middle, then this would have been negative 21, which means 21 years ago, right? Not 21 years in the future. Example number 4. I would like you to try this one, of course. The question says a radioactive substance has a half-life of 80 years. A, what percent of a same of the substance would be left after 200 years? B, how long would it take before 30% of the sample remains? C, how long would it take before 60% of the sample decays? Pause the video, try this. When you press play again, I'll be here. Welcome back. Here's the first part. Again, if you think about part A, you want to start with the formula. A equals to I times b to the power of t divided by p. Again, this is how you can start with exponential growth, exponential decay. It depends on the context. So half-life means the substance will have half as much, which means b is going to be 1 minus 0.5. Now, of course, you can write down half if you like, which stands for half-life, but the concept is you take 100% minus 50%, which is 1 minus 0.5. Now, what is the half-life? It's 80 years. So that means 80 years later, you have half as much. Another 80 years later, you have half of the latest amount, and so on. So that's why the period is going to be 80 years. Now, we don't really know exactly what we're starting with, so all we have is I. In part A, they're asking what percent of a same of the substance will be left after 200 years. So, we're just saying, all right, we have 200 years, which is time. And you want to find out, 200. You want to find out what is the percentage. So you leave it in terms of I, and that's totally fine. Again, this is the same as half to the power of 200 divided by 80. You can cross out the 2 zeros. 20 divided by 8, you can leave it as is. If you grab a calculator, you can reduce it if you like. It's up to you. Now, if you grab a calculator and you work it out, look what happens. This is going to be half to the power of 20 divided by 8. Now, this is going to be approximately 0.176776695. I'm going to write down 0.177 times I. Remember, percentage. Percentage means you have to multiply this by 100. So this is going to be approximately 17.7%. And I means, of the original amount. So again, you can write a final statement if you like to verify this, but it's roughly 17.7% of the original amount. So I'm going to write down FS for final statement. You can write that, of course. Part B, how long will it take before 30% of the sample remains? So think about the beginning. Again, A equals to I times B to the power of T divided by P. Now, 30% of the sample remains. You start with I, but in the future, you're going to have only 30%, which is 0.3. If you want to write down 0.30, that's fine, of the original amount. Again, half-life means half. So I'm going to write down half this time instead of saying 1 minus half. And your goal is to find out how long, meaning you want to find time. Now, we do know the period is going to be 80, so it's going to be like that. Again, the first step is you can cross out I on both sides because I divided by I is 1. As we're doing this, remember, you have to log both sides. That's the only way of solving it. So if you write down 0.3, which equals to half to the power of T divided by 80, don't forget, you have to take the log of both sides. The reason we do this is because the exponent could be brought to the front. So again, in the next step here, you can write down log of 0.3, which equals to T divided by 80, multiplied by log of 0.5. To find time, again, I'm going to round this with you. Let me create some space first. This is going to be T equal to, the opposite of dividing by 80 is to multiply, so 80 times log of 0.3 divided by log of 0.5. Again, this is going to be approximately, let me grab a calculator, work it out. 138.9572475. I'm going to round this to 138.96. It's going to be years. But again, as we mentioned, you always want to round up. So if you round this to the nearest whole, if that's the expectation, then you can say approximately 139 years. Part C, how long would it take before 60% of the sample decays? So same structure. Again, you can write A equals to I times B to the power of T divided by P. The only difference is you're looking for 60%, which is 0.6, or 0.60 times I, which equals to I, times, again, half-life means 0.5. Time is what you're looking for, and it's going to be divided by 80. So I'm going to create some space. Let's try this one more time. So again, the first step is you can divide both sides by I, or you can simply cross it out. So if I grab a different color for your reference, I'm going to cross out I and I. Now, you have to log both sides. So I'm going to take the log of 0.6 on the left, log of 0.5 to the power of T divided by 80 on the right. Again, you can bring the exponent to the front. So log of 0.6 equals to T divided by 80 times log of 0.5. If you isolate for time, the opposite of dividing by 80 is to multiply. And of course, the opposite of multiplying is to divide. So you're going to divide by 0.5 or log of 0.5. Let's grab the calculator. We'll talk about the rounding again. 80 times log of 0.6 divided by log of 0.5. That's going to be approximately 58. Let's pause for a moment. Let me just go back and double check. Now, as I'm double checking this, I'm going back and I recognize this one thing. 60% of the sample decays. Really means 40% of the sample remains. So I'm going to go back and make this correction, everybody. So as you can tell, there's no answer key. I'm doing this with you in a live session, and I can tell I made this mistake. So this should be 0.4, by the way. That was my mistake, everybody, because 60% of the sample decays means 40% of the sample remains. So all I need to do is go back and just update this. It's not a, you can still follow up, and it's the same structure. The only number is 0.4, not 0.6. Let me try this one more time. I'm going to grab a calculator and redo this entire calculation with you. So I'm going to take 80, multiply by log of 0.4 divided by log of 0.5, and I see 105. Let me just go back to the same color for your reference, 105.7542476, or I can round it to 75 years. Now again, when it comes to time, I'm going to round it to 106 years, just because this would definitely give you that amount. And of course, you can write a final statement on your own. Second last example, example number 5. A population doubles every 15 years. Determine the yearly growth rate. Again, you can pause the video, try this. When you press play again, I'll be here. Welcome back, everybody. So again, the first step is to recognize that A equals to I times B to the power of T divided by P. So we're going to translate this one sentence at a time. If a population doubles, again, it's really 2, but if you write down 1 plus 1, that's fine. 1 means you're adding it by 100%, which gives you the doubling factor. And this happens every 15 years. So it's going to be 15. Now, actually, let's go back. See, nope, that's not true. I'm going to go back and translate this again. This double doesn't mean double in terms of the rate, because you want to find the rate. I'm going to go back and do this one more time. Yearly growth rate means you want to find A. So you're actually looking for B. I'm going to go back and do it again. Double means if you start with I, you get 2 times I. So if the population doubles, you're going to get 2I. If the population triples, you're going to get 3I. If the population is 10x, you're going to get 10I. And it's going to be B, which is what you're looking for. That's the yearly growth rate. And this happens every 15 years. So you can just say 15, just like that. Okay. So again, the opposite of multiplying by I is to divide by I, or you can cross out the 2 i's from each side. 2 equals to b to the power of 15. The opposite of to the power of 15 is you take each side to the power of 1 over 15. So again, I'm going to grab the calculator. I'm going to try this. This is going to be 2 to the power of 1 divided by 15. And this is going to be 1.047294123. Now, you got to be very careful here, because when we say the growth rate, you're really looking for R. You're not looking for B. So growth rate really means R. But we define this as 1 plus R. So you want to be mindful, right? You're not looking for just the value for B, but you're looking for R. So if this equals to 1 plus R, what you're saying is that R is going to be the left-hand side minus 1, which is approximately, if you round it to 1 decimal in terms of percent, it's going to be 0.047, or approximately 4.7%. So again, don't forget, you're looking for the annual or the yearly growth rate. You're not looking for the value for B. All right, great starter, great finisher. I would like you to read this by yourself and try it. And when you press play again, I'll be here. Welcome back. Here we go. So if you look at the given, again, you can say the following. There's a car, and it's $15,000. It depreciates by 70%. So again, you can say A equals to I times B to the power of T divided by P. And it says how many years would the car be worth? Only 500. So the future amount is going to be 500. The car was purchased at 15,000. Since it depreciates, each year the value of the car depreciates to 70% of its value. So it's going to be 0.7 to the power of, and you want to find time. So it's going to be like that. So again, the opposite of multiplying by 15,000 is divide by 15,000. On the left-hand side, that's going to be 5 divided by 15 is going to be 1 over 30, which equals to 0.7 to the power of t. You have to log both sides in order to find time. Don't forget the exponent can be brought to the front. So log of 1 over 30 equals to t times log of 0.7. So time is going to be log of 1 over 30 divided by log of 0.7. I'm going to grab a calculator. I'm going to work this out with you. We're going to express this in terms of years. So log of 1 over 30 divided by log of 0.7. This equals to 9.535846124. I'm going to round this to 9.54 years. So sometimes you can round to 2 decimal places. I still round it up, by the way, just like that. I hope this makes sense.